Hello, welcome to session 2 on ARM Cortex. In last session, we have discussed about the fundamentals of assembly language programming. In this session, we'll discuss the various instructions available in the instruction set of ARM Cortex M3. Let's begin. So first we'll look at 16-bit processing instructions. Here you can see there are two add instructions, add C and add. Add C adds with a carry and add is simple addition. If there are two registers R0 and R1 which are performing the add operation on them, then add C will add the R1 plus R2 and also adds the carry to the result of R1 plus R2. Whereas in only add instruction, it only adds R1 and R2 and it does not consider carry flag in addition. However, there is another register add R. This is add PC and an intermediate value and put the result in a register. So there will be one intermediate value which will be added to PC and then that result value will be put in a register. Then we have a logical AND which performs a AND operation. So whenever two bit streams are given, 16-bit, so there will be a AND operation performed and the result will be stored in the register, destination register. Then ASR, arithmetic shift right. So it will shift the bits to right side. So when we shift the bits to a right side in a register, it is as good as we are dividing the value by 2, and when we shift it to the left, it is multiplied by the value of 2. Then we have a bit clear to clear the bits and also bit clear. Basically what it does is it performs a logical AND on one value with the logic inversion of another value. That's what it does. So all the bits will be cleared by doing that. Compare negative. So this will consider a negative flag which is available in the CPSR, and it will compare the data with 2's complement of another data and update the flags. When we are taking a 2's complement, it is as good as we are considering a negative value of a number. So that is why it's called as compare negative. Then we have a simple compare, that is just comparing the two values in a register, and it will update the flags in the CPSR. Then we have a copy instruction available from architecture V6 version. More value from one high or low register to another value, high or low register. That is copying from the higher side to the lower side of a register. It is similar to move instruction, but it can also be used in some cases for copying. Initially in a V6 it was there, but however instead of using CPY directly we can use move also. Then next is exclusive OR, that is a XOR operation. So if both the bits are same, the result will be 0, and if the two bits are different, then the result will be 1 in case of XOR. Then logical shift left and right, that is shifting the values to the left or right, but here the values will be through flag registers. So that is carry flag. In arithmetic shift is slightly different from these logical shift in that sense. Then we have a move register, can be used for a register to register transfer or loading a immediate value. Immediate value is when we give a value in the instruction itself by prefixing the value with the hash symbol. that we call as the immediate value, or it can be used to transfer the value from one register to another register. Then multiply. So this will multiply the two registers, the value contained by two registers, and the result will be stored in the both the register depending on how many bits of the results will come. If the result is of only 16 bit, then only destination register is used. If the result is 32 bit, then a higher bytes of the registers are also used. Move not, it actually transfers the inverted value. In a normal move operation, we just transfer all the bits as it is. But in MVN, that is move not, the inverted value of the register is moved to another register. Then negating the values, that is obtaining a 2's complement, that is negating the values. Then we have a logical OR. So this is another logical operation. Already we have seen AND and XOR. This is a third operation which performs the OR operation. If any one of the bit is 1, then the result will be 1 in a OR condition. Then reverse subtract. So the subtraction registers are reversed in this case. How the subtraction has to be done, that is reverse subtract. Then rotate right. So it is rotating all the bits to the right. So when we rotate, it will go through the carry flag again. Then we have two subtract instructions. One is subtract with carry, another one is direct subtraction. For subtraction, we usually call the value to be subtracted is called borrow. It is not called carry, but in microcontrollers, we don't have a separate flag for the borrow bit. The carry flag itself will be used as borrow and the operation will be performed. That's why the instruction is called subtract with carry. Then we have a normal carry or normal subtract which does not consider carry into operation. Then we have another instruction, test instruction, used as a AND operation, and zero flag is updated whether the result is if all the bits are zeros or ones, that will be checked and that the result will be stored. So zero flag will be updated, but and whatever the operation is performed, that result will not be stored. Then we have a reverse 16. It is again now from the V6 version. Reverse the byte order in 16-bit half word. Higher 16-bit is made lower 16-bit and lower 16-bit is made to higher 16-bit. That is 16-bit exchange. Then reverse SH, that is reverse the byte order in lower 16-bit of a half word of a 32-bit register and a sign extend to the register to 32 bits. That is reverse HH, or reversing the order of the half word and extending the sign bit. In the previous instruction, it is only reversing. Here it is sign bit is extended. Then signed extend byte, available again from the V6. So it is extending the sign bit of the byte. Next instruction extending the sign bit of the half word. So both are quite similar. One is of a byte, another is the half word. Then next instruction is unsigned extend byte, again available from V6. And next one is unsigned extend half word, again from V6 version. So as the explanation says, it is extending unsigned value, whatever the value is there in the MSB, that is a sign bit. If it is an unsigned value, then the higher bits will be padded with 0. As all the registers in R bar 32-bit, even if you are operating on a 16-bit values, then the register will have 32 bits. So 16-bit will be the value what is given for the register for the processing, and a higher 16-bit should be padded either with a 0 or with a sign bit. That depends on the instruction what we use. Either we can extend a sign bit by using X SXTB and SXTH, or we can extend the unsigned bit from UXTB and UXTH. So therefore instructions are used to extend the bit of the MSB to the higher half word. Then we have some branch instructions, that is 16-bit branching. So first, only B single character shows unsigned or unconditional jump. It does not have any condition. So it will branch to the label mentioned in the instruction. Then we can also have a conditional branch. So whatever the conditional bits we have, carry, 0, negative, overflow, there are 4 conditional bits available. So this conditional branch can be done with any of these 4 bits. Then branch with the link. So this branch with the link is done whenever there is a subroutine call. Then the link register will be used to branch, and this will be actually 32-bit instruction, but however also available in the traditional thumb ARM processors. Then BLX, branch with link and change the state. Here the state is CPSR. The state will be changed and it will be branched. Again, BX is branch with exchange of the state. When we branch to other mode of operation from user mode to supervisor mode or any other mode, then the status will be exchanged when BLX is used. Then branch with exchange state. Here only exchange operations performed, but link register is not used. That is BX. Then we have CBZ, compare and branch if 0. As I said, any conditional flag can be used in conditional operation. That is carry flag, 0 flag, negative flag or overflow flag. Any of these conditions can be used. So CBZ is combination of 2 instructions. One is compare and branch. Both operations are done in a single instruction. Similarly, we have CBNZ, which is compare and branch if non-zero. One is for 0 and another one for non-zero. Similarly, we have IT instruction which perform the operation of if then. As in the C programming, we use if then for a conditional checking. Like that, here also IT instruction can be used to check the conditions. Then we have load store instructions, LDR, LDRH and LDRB are load instructions. So load a word from a memory, load a half word from memory and load a byte from memory. So whether the 32-bit data is used, 16-bit data or a 8-bit data, depending on that, LDR, LDRH and LDRB are used. Then we have some more 16-bit instructions. That is, one is supervisor call, that is SVC. Whenever we want to call an instruction from a system, then we use a supervisor call. When we want to send an event, especially these things are used when you are getting into more of a hardware interfacing using the assembly language, then we have to go for supervisor mode and send an event which has happened. So event driven operations to be performed. In those cases, these instructions are used. However, for general simple programming, these instructions are very rarely used or they are not used at all. Then is sleep and wait for event. So again, this is event driven operations. So it is waiting for an event and then SCV instruction presents the event on the occurrence. Then WFI, that is wait for interrupt. Sleep and wait for interrupt. The sleep operation is performed to reduce the power consumption, and whenever interrupt comes or an event happens, the operation is performed. WFE and WFI are very efficient instruction in that sense. Then we have a Bkpt, that is breakpoint. If debug is enabled, then this uses a breakpoint. The breakpoint stops the execution and allows us to see the status of the program at that instant of time. For that, we use a breakpoint. It is very much helpful in debugging the program. Then we have NOP operations. No operation, it does not perform any operation. It is just used to cause a simple delay programs. We use NOPs. Then enable primary mask and enable primary, disable primary mask, CPSIE and CPSID, enabling and disabling the mask registers. So masking is basically stopping the interrupt is one type of masking. If we don't want any interrupt to arise when the program is being executed, then they can be masked or disabled. And whenever we are ready to receive the interrupt, then they can be enabled or unmasked. Then we have some 32-bit instructions. That is again data processing. Here again the instructions are quite similar to what we already discussed. Add C add for performing addition. Add W is one suffix W is added to indicate it's a wide operation, that is 32-bit operation. So add W is used. Add ER, again add PC to the immediate value and put the result in a register. Already we discussed about this. Then logical AND operation is there. Arithmetic shift operation. All the operations are same, but only the thing is they are operating on 30-bit data instead of 16-bit data. BFC bit field clear and BFI bit field insert. So any particular bit can be modified in a register using BFC and BFI. Similarly, if all the bits are to be cleared, then BIC is used to clear the bit. Then compare negative. Here the comparison is done for 32-bit value and the checked whether the number is negative. Compare negative, that is the negative value will be compared. So again 32-bit data processing instructions. Compare to data and update the flags. CMP will update the flag. But the result of the comparison will not be stored anywhere. Only the flags will be updated. CLZ, count leading to 0. You can check whether the count is leading to 0. Then this is indicated by 0 flag. So 0 flag will be checked in this. Then we have exclusive OR. Again, as I said, if both the bits are 0, the result will be 0. If any one of the bit is 1, the result will be 1. If both the bits are same, the result will be 0, whether it is 0, 0 or 1, 1. If the two bits are different, then the result will be 1. Then similarly, we have logical shift right and logical shift left, LSL and LSR, shift right and shift left, that is logical operations. Then we have one more instruction called MLA, multiply and accumulate. This is one very important instruction if we are performing the operations related to signal processing or image processing. Then this will help a lot in solving certain series of operations. In mathematics, we come across those series in especially signal processing applications. There it will be used extensively. Then we have multiply and subtract is also there. So that's another very specific instruction. So first it will multiply and then subtract the value. So this is a combinational instruction. Multiply and subtract. So what value has to be subtracted is also mentioned in the instruction. So two registers which are operand, the operand value will be multiplied and whatever the value is given for the subtract, that value will be subtracted, either immediate value or the register value. Then move operation to transfer the data from one register to another register or from the memory to register. Then move W, perform a immediate wide operation. It performs a 32-bit operation. Move top, write an immediate value to the top half word of a destination register. If the 16-bit value is given, then the value will be written to the top half word of the register. That is starting from bit 16 to bit 32. Then we have move negative. Negative value will be moved, that is 2's complement of the value available in the source register will be transferred to destination register. Then we have multiply. MUL performs the multiplication. Logical OR, that is OR operation. If any one bit of the operand is 1, then the result will be 1. Then logical or not. It performs or operation and not operation both simultaneously in the same instructions. Reverse bit, all the bits will be reversed. All the ones will become 0, zeros will become ones. That is reverse bit. Then we have reverse word. So word reverse is exchanging the word. Byte reverse, packed half word. Byte reverse, signed half word. Packed half word is all the higher half word will be paired with 0, and in the signed half word higher bits will be extended with the sign bit. So they will be reversed. Then rotate right and reverse subtract. Rotate right, again as we already discussed, it is going through the carry flag, and reverse subtract is subtracting the other way from the conventional subtract operation. Then some more bit processing instructions like Rsb Reverse Subtract, already we have seen that. Then rotate right, extended. So it is rotating right, and if the bits are extended to 32-bit, as there are 32-bit processing values. SBC subtract with carry, as I said, carry is nothing but a borrow. We don't have a separate specific borrow bit, so carry bit itself will be used as borrow for subtraction. SBFX, signed bit field extract. Whatever the signed bit is, that is extracted and used in the instruction. SDIV, signed divide operation. So quotient, remainder both will be stored in 2 registers. So both will be available, quotient and remainder. Signed multiplication and accumulate, SMLAL. Already we have seen what is the multiply and accumulate. So this is performed with the signed operations or the signed operands. Then signed multiply long, that is 32-bit values will be multiplied along with the sign bit. SSAT, signed saturate, the value will be made to the highest value or the saturated value, that is signed bit will be signed saturate. Subtract with carry, SBC, the instruction has been repeated. SUB, that is simple subtraction. SUBW, subtract white. And SUXXTB, signed extend bit, sign extend half word. Already we have discussed all these 4 instructions. TEQ is test equivalent, used as a logical exclusive OR. Flags are updated but result is not stored. That is test equivalent if the numbers are equal in 2 registers. Test, again it performs a logical AND, but it does not store the value. Flags are updated however, so that flag can be used to check the condition. Then UBFX, unsigned bit field extract, and unsigned divide. There is a signed division as well as unsigned division. UDiv is unsigned divide, SDiv is signed divide. Then similarly we have unsigned multiply and accumulate and unsigned multiply long. Similarly also we have unsigned saturate. So these are only unsigned operations, unsigned extend byte, unsigned extend half word. So these are our unsigned operations. Similarly the analog similar instructions are available in the signed operations also. So these are some important instructions. Other than that, we have load store instructions. Other than the 32-bit processing, these are the load and store instructions. LDR, LDRT, LDRB. These are similar instructions. The only thing is the way they access the memory. LDR, load a data from memory to register. LDRT, load a word data from memory to register with unprivileged access. It is only access privileged or unprivileged, that's a difference. Then we have LDRB, load byte data from memory to register. LDR is load word data, LDRB is load byte data. Again we have LDRBT, load byte data from memory to register with unprivileged access. So in the successive sessions we will see what is privileged and unprivileged values or accesses or modes of operation. Similarly, we have LDRH, which is a load word, half word, and LDRHT, load half word data from memory to register with unprivileged value. So totally there are 6 instructions with the word operation and half word operations. Then we have LDRSB, that is load byte data from memory, sign extend it and put it to the register. In the same instruction, we are performing the sign extension as well as loading operation. In the next instructions, LDR SBT, load byte data from memory with unprivileged access, sign extend and put it to the register. Then we have LDRSH, load half word of a data from memory, sign extend it and put it to the register. LDRSHT, load half word data from memory with unprivileged access, sign extend and put it to the register. So operations of all the instructions are quite similar, only there will be a small difference from each other. And then we can see LDM or LDMIA, load multiple data from memory to register. Simultaneously we can load more than one data. So for that we'll be using LDM. Then LDMDB, load multiple decrement before. So it will be loading the multiple value, but the values will be decremented before it is loaded. Then LDRD, load double word data from memory to register. Double word data, that is 64-bit data. STR, store word memory, word to the memory. Then these are all store operations. Till now whatever we discussed, they are all load instructions. These are store instructions. STR is a store to memory, stores the word. STRT, store word to memory with unprivileged access. STRB, store byte data to memory. STRBT, store byte data to memory with unprivileged access. Then again STRH, store half word data to memory, and STRHT, store half word data to memory with unprivileged access. STM or STMIA, store multiple words from register to memory. We have to mention all the registers or auto increment registers and store the value in the memory. Then some other instructions they are STMDB, store multiple and decrement before storing. As I said, the same auto increment or decrement can be done. So in STMDB, the decrement will be done before storing. STRD is store double word data from register to memory. Double data is stored to the memory. Push and pop, these two instructions are used in the stack operation. Whenever the control is moving from the calling program to called program or calling function to called function, the push operation is performed, which stores the registers into a stack memory. And when the control is coming back from called program to calling program or called function to calling function, then the status of that register will be retrieved. And then program continues from where it has stopped before going to a subroutine or a function. Then again we have similar to 16-bit, here we have 32-bit branch instructions. So B, that is the unconditional branch. Again we can use a conditional branch with all the conditional flags, 0, overflow, negative and carry. Then branch with link, so link register will be updated. TBB, table branch byte. So this is forward branch using a table of a single byte offset. So whenever we have a table of operation, this can be used. So it will be moving in the table with a single byte offset, or TBH is a half word offset. So base will be pointing to the start of the table and the offset has to be maintained in terms of byte or a half word in the respective instructions. So these are some very important instruction in ARM. However, other instructions which are the 32-bit instructions are LDREX, exclusive load word, exclusive load half word, and exclusive load byte. So to load byte, half word and a word, we have 3 load instructions. Then we have similarly we have store instructions for that, exclusive store instructions for all the 3, that is byte, half word and word. STREX, STREXH and STREXB. By default, it is taking word. Only in the extension H and B will indicate whether it is a half word or a byte. Then clear EX, clear the local exclusive access record of a local processor. Whatever exclusive access was given to a local processor, that will be cleared. Then MRS, move special register to GPR, general purpose register. Then MSR, move special register from general purpose register. That is a values transferred to or from the general purpose register. That is special register to GPR or GPR to special register. Then again NOP, no operations. Then SCV is send in event. Already we have seen that. WFE is sleep and wait for an event. WFI is sleep and wait for interrupt. Already we discussed both of them. ISB is instruction synchronization barrier. This one is used for the synchronization of the processes in the higher level of programming. Then DSB, data synchronization barrier, and DMB, data memory barrier. In the coming session, as and when we come across the programs using these instructions, we'll discuss them in detail. Then we have some description related to Cortex M3. Already we discussed moving the data between register to register, moving the data between memory to register, and moving the data between special register to register, and moving a immediate data value to the register. These are the operations which will be performed in the instructions. The exclamation mark in the instruction specify whether the register should be updated after the instruction is completed. That's what it indicates. You can see in the example, if an exclamation mark is given, the destination register is updated, otherwise it will be unchanged after the operation. Then these are some descriptions of the instruction, what they perform with the details, how do they read to a particular register, and using an offset. So whenever we use an offset, basically there will be two registers used, base and offset. In all these instructions, what is shown here, the Rn register is taken as a base register, and then the offset is provided. So base register value is added to offset to get an actual or a physical value. Then the operation will perform to that location. Similarly, here we have some more instructions. So multiple memory access instructions, how they are performed. So as we already know, read multiple word from memory locations specified by RD, and increment after each transfer. Similarly, here you can see store multiple words to memory locations specified by RD, address increment after each transfer. So we need not explicitly increment the values of a register to point to a next location in the memory. Instead, in a single instruction, we can perform both transfer as well as increment operations. So the programming will become compact and code density can be increased. Then we have load register, that is a wide operation. .w indicates a wide operation, that is 32-bit operations. The operation is same, only if there is no suffix given as a .w, then 16-bit operation is performed. If the .w is given, 32-bit operation is performed. That's basically a .w meaning. Otherwise, the operations are storing and loading the data. Some more instructions, common controller CMSys. So CMSys is a common microcontroller software interface standard. So you can see here what are the target processors available in the different CMSys and description related to that. So these software interface standards are used to program different types of softwares, whether the software is used for a normal real-time applications or interfacing applications or a DSP applications or a device driver development application. Depending on that, the respective processors are used and they will be programmed to operate in those applications. That means these particular CMCs will provide, those interfaces will provide related functions to perform the operations in those applications. That is what a CMSys means. Thank you. End of session 2.